Last time on graph theory, we began exploring single source shortest paths by looking at Dijkstra's algorithm. We learned that it has a flaw, and that is the fact that it couldn't actually process graphs with negative weight edges. Today, as promised, we're gonna look at an algorithm that can, called the Bellman-Ford algorithm. You're watching another episode of Graph Theory. Hello and welcome back to Graph Theory. Today, we're going to be looking at the Bellman-Ford algorithm, which performs single source shortest path computation on a directed weighted graph. So notice that we have one additional constraint today, and that is the fact that our graph needs to be directed. Of course, that is not a huge issue because if you actually have an undirected graph, you can turn it into a directed graph by simply doubling up every edge in both directions. So basically what you end up with is two directed edges to replace one undirected edge. As we've mentioned earlier, Bellman-Ford algorithm is more robust in the sense that it can handle a graph with negative edge weights. This is of course unlike Dijkstra's algorithm, which cannot. However, generally Bellman-Ford algorithm is slower than Dijkstra's algorithm, which is why you don't want to do this unless you are not sure if your graph has negative edges. If you are sure that it doesn't, then use Dijkstra's algorithm because it's faster. The reason why the Bellman-Ford algorithm is able to handle negative weight edges is because of the fact that it basically searches exhaustively. This is unlike Dijkstra's algorithm, which visits every edge just once. In Bellman-Ford algorithm, what you do is you actually keep going back and looking at all the edges again. So you actually have to go through your graph many times in multiple passes. That is the major difference between Dijkstra's algorithm and Bellman-Ford algorithm. And for Dijkstra's algorithm to work in one pass, it needs to be very careful about which edge it explores next. If you remember our trace from the previous episode, Dijkstra's algorithm always looks at a vertex with the minimum distance, and it basically, keeps going from the vertex of minimum distance. In the Bellman-Ford algorithm, we don't care. We actually take on the edges in any order, because we know we're going to go back later and do the same thing again. So those were the differences between Bellman-Ford algorithm and Dijkstra's algorithm. In fact, for the rest of the computation, they are very similar. I would go so far to say they're exactly the same. So the difference between these two algorithms lie in when they do certain things. What they actually do is the same. So with this preface in mind, let us jump into a trace of Bellman-Ford algorithm. Just like last time, basically this algorithm is quite long, so we've broken them up into several steps, which we will see as it comes. Bellman-Ford algorithm can be broken down into 3 steps. The first of which, of course, is just initialization of all the data structures we need. In this case, we are just creating several arrays, as well as setting the distance of our starting node to 0. So this is very standard stuff. You should basically be expecting this. So let's go ahead and draw everything into our diagram itself, allowing us to move on to step 2, which is the actual part of the algorithm where we will do all the work. Notice right off the bat that we have several nested loops over here. In fact, we're going to be doing a lot of work. As mentioned, Bellman-Ford algorithm is more or less like a brute force algorithm. So yeah, this shouldn't surprise you too much. So basically, we're gonna have to run our main logic as many times as there are vertices, which is why I have a little indicator down here that says, well, we have to do 8 iterations in total, and we are looking at the first. So let's begin with the actual trace itself. For every single edge in a graph, we're gonna basically look at the 2 vertices it connects, and very similarly to what Dijkstra's algorithm does, we will try to push the weight forward and then check to see if that new weight is actually better than what we have recorded. If it is, then we will go ahead and update the distance and the parent. So yeah, this is exactly what Dijkstra's algorithm does. Just that now, we don't really care what is the order of the vertices we visit. So yeah, basically we can just trace on, and the order I'm going to actually visit all the edges in is from top left to bottom right, which is why, well, we're going to do this top chunk first from left to right, and then we're going to move on to do this chunk from left to right, before finally doing these. I should mention at this point that that is a completely arbitrary order that I have chosen, and you can really tackle this in any order. It doesn't matter, because that is how this algorithm is built. So yeah, basically what we do at this point is just go to every node and try to propagate its weight forward. Of course, in a case like this, trying to propagate its existing weight forward, 5 plus 3 gives us 8 over here, and that is not more optimized than the weight we already have, which is 6. And that is why this conditional evaluates to false and this code doesn't run. This is exactly like Dijkstra's algorithm. So yeah, I've colored this red to say that we are visiting this edge and we've decided not to do anything about it. So yeah, basically, well, I'm just going to move forward pretty much as quickly as I can because there isn't really too much to speak of. So what we've just done is we have finished our first pass. In fact, somewhere along the way we have kicked out an edge and replaced it with a cheaper one. Of course, as mentioned earlier, Bellman-Ford algorithm works best for when there are negative edges, which is why I've injected a few and we can see how it all works. Anyway, we've finished our first iteration now, and as you can see, well, we are not quite ready to stop yet, because we have a very cheap node here, and we will probably benefit from making better use of it. Which is why, of course, we now have to begin on our second iteration. So yeah, it's our second iteration. We're going to visit all the edges once again, and we'll see how things change up in our second iteration. So in fact, the vast majority of the edges don't change, except this, now that, this is cheap. So this gets updated as well, because of course D is cheap, causing B to be cheap, which is why the edges leading out of B are worth considering. So yeah, as we move on, we also realize we're looking at this edge here. Even though this relation has not changed, but we are now updating the weight here. As you can see, if I were to go back to the previous slide, the weight was 8. But based on what we know at this point, despite the fact that this edge is still the best, well, it can now give you a cheaper weight, which is why I've colored it green to mean that we are still using the same edge, but we are updating the weight. So yeah, if we were to continue on, we will notice that there isn't too much to change, and that's it for that iteration. So we proceed into our third iteration, and I want you to notice one thing. Every single edge that we visit actually doesn't have any more changes. So we've just visited the very last edge of this iteration, and we realize that we haven't changed anything within this iteration. Now, we can of course go on to the fourth and the fifth iteration and so on, but every one of those iterations will do the same thing as we've just done. In other words, they will be equally useless as the iteration we've just done. And that is why, in fact, we can actually make an optimization in this part of the code. By inserting a flag outside of the inner loop, basically what we can do is we can actually check to see if changes were made during that particular iteration. If we find that no changes were made, we can actually break out of the outer loop. So yeah, in fact, this is how we can terminate early. In fact, as you saw in our previous trace, we only needed 3 full iterations to know that we don't have to do any more work. Anyway, with steps 1 and 2 done, we can move on to step 3, and that is to check to see if there is a negative cycle. All we are actually doing here is we are going to just visit every single edge again and perform the same logic. If we find that at any point there are still improvements to the shortest path tree, that actually shows us that there is a negative cycle. Now, at this moment, it's probably not very clear how or why this works, but as we move on, we'll understand why. First of all, let's try to understand why a negative cycle is so harmful, and why Bellman-Ford is actually unable to resolve having a negative cycle. First and foremost, what is a negative cycle? Well, it's what we have right here between B, C, and D. Notice that if I were to go from B to C to D and then back to B, Well, first of all, that is a cycle. But more importantly, it is a negative cycle because the total edge weight adds up to -8. So in order to see why this is an issue, we're going to try and evaluate shortest paths on this little graph without using any algorithm. We're going to try and do this completely intuitively. So let's say what I want to do is I want to find my way from A to C. So obviously I can do that by going through B directly, and the total distance to C is 3. But the question is there a shorter path? Are we able to get to C by incurring less distance? Let's try this out by visiting D. When we visit D, the weight is now -2. This allows us to update the weight at B to -7. When we go from B to C now, the weight is now -5. So yeah, we can actually go from A to C by incurring a weight of -5, which is lower than what we had before. Now, is there a shorter alternative to this? Turns out, if we go and visit D again, and then back to B and come back, we now have a weight of -13. Do you see the problem here? Every time we end up at C, we can always go through the D to B and then back to C again to get a lower weight at C. And we can do this indefinitely. We can do this an infinite number of times until everything goes to -infinity. So that is why negative cycles are a problem, because the algorithm can never terminate. And that is why Bellman-Ford algorithm needs to check to see whether there are negative cycles. So what we've just seen is half enough to explain what we're trying to do here, which is to say that if we already know that we are done with the algorithm, and yet we find that we can reduce the edges further, then that is a sign of a negative weight cycle, and that is why we can throw an error. However, what is not clear is, if we were to go back to step 2, why is it that iterating as many times as there are vertices is definitely enough for us to know that the algorithm can terminate? This requires a little bit of additional explanation, so bear with me. Now do remember that when we trace this algorithm, the edges can be picked in any order. What this means is at the end of the first iteration, we are only guaranteed to find paths that are 1 edge long. We are not absolutely sure that we have found longer paths yet. Of course, it just happens for this particular graph that we have found our shortest path tree that leads to every node. But yeah, we can really only guarantee this for paths of edge 1 starting from the source. So of course, applying this same logic moving forward, at the end of iteration 2, we can be sure of paths of length 2, once again starting from the source. So on and so forth. Now for this particular graph, our longest shortest path is actually length 4. Of course, in the worst case, a longest path would only be as long as the number of nodes in the graph. The reason is that assuming there are no negative cycles, then adding more vertices to your shortest path can only make it longer. So yeah, there's no point picking redundant vertices, and what this means is the longest possible path must only be of length v. And that is why we only need to iterate that many times. In fact, if we were to check after that and find that we can still improve the distance, then it must tell us that there is a negative weight cycle. So yeah, this should explain the thought process behind step 3 of Bellman-Ford algorithm, as well as why we have that number of iterations in step 2. Now that we've seen the trace in action, now that we've understood the terminating condition as well as the destructive effect of negative weight cycles, it is time to wrap up this episode by talking about the time. Now, step 1 involves initializing data structures, and this of course depends entirely on the data structures you've selected. Unless you're using some really ineffective data structure, you should be able to get OV time. In this particular case, because we're using arrays, then yes, it'll be OV time, because we have to loop through and set v values in these arrays to infinity and null respectively. Step 2 is OV times OE. The reason for that is of course because we have an OE for loop nested inside an OV for loop. The actual contents of the loops are of course data structure dependent. Doing things like, looking for neighboring vertices could take a lot of time or very little time, depending on the graph data structure you've selected. Step 3 being basically like just another iteration of step 2 will of course simply take OE time multiplied by however long it takes to do the things you need to do within the loop itself. A very common time complexity for Bellman-Ford is OVE. The reason for that is step 1 being taken as OV, step 2 being taken as OVE, bearing in mind that the actual relaxation part, in other words the part where you basically look for a new distance and see if you need to change it up, that is normally taken to be constant time or 1, and of course if we were to use arrays like we're doing here, then yeah, that is indeed O1. Same deal for step 3, the contents of the loop itself is O1, the loop itself is OE. So yeah, when you sum all these things together, obviously OVE is the one that grows the fastest. OV and OE grow slower. And that's why using the big O notation, we drop both these terms, keeping just OVE. And that is why Bellman-Ford algorithm is most commonly considered an OVE algorithm. And there you go, that is the Bellman-Ford algorithm. I hope this episode didn't run too long for you, I hope it was still okay. But well, moving on, next time we are actually going to switch gears to look at topological sorting. So hopefully that will be, a nice refreshing change because that is a little bit simpler than what we're doing now. Anyway, that's all there is for this episode. Thank you very much for watching. Until next time, you're watching 0612 TV. Thank you very much for watching. If you liked this video, consider checking out the rest of my work on my channel. Alternatively, you may want to check out a playlist of the other videos in this series. If you'd like to show me some monetary support, I am on Patreon. You can find a link to my campaign in the video description. Of course, you can simply like this video or leave a comment. I'll be sure to respond as soon as I can. To keep in touch with my future uploads, do subscribe to this channel. And for even more updates, check out the official Twitter account for this channel at 0612TV. Thank you for your support.